The nucleophilic aromatic substitution reaction is the substitution of a leaving group on an aromatic ring that's activated as a leaving group by having either a para or ortho electron withdrawing group. So EWG is electron withdrawing group, LG is the leaving group. So I could have both of these situations where it could be in the ortho position with the electron withdrawing group. And what happens is the nucleophile comes in and the net result is replacement of that leaving group with the nucleophile. So this is just a general overview of how this reaction is and what the byproducts are. So this would be the nucleophile would come in here and the electron withdrawing group would be here. All right, and the leaving group would obviously be the leaving group minus. Okay. When I try to do this with a meta-substituted, so I'll have the leaving group here and the electron withdrawing group is in the meta position, and I add a nucleophile, we get no reaction. So when we go through the mechanism, you'll see why the meta doesn't work. Meta leads to no reaction. Both the para substituted and the ortho substituted lead to these nucleophilic aromatic substitution reactions. All right, so let's take a look at the ortho one first. And I'll do a very specific example. So I'll have a bromine next to a nitro group. So the bromine is our leaving group, and the nitro group is our electron withdrawing group. And I'm just going to use OH minus as the nucleophile. And the product is going to be this substituted phenol after working it up plus the Br minus. So how does this reaction happen? Let's go through it. What happens is we get addition to the aromatic ring and the electrons go onto the carbon next to the electron withdrawing group. This is really why the reaction happens. So the OH adds in, and I wind up with a negative charge next to my electron withdrawing nitro group. And this is actually a good thing, right? Having that electron withdrawing group there is good for it. I have all these resonance structures within the aromatic ring, but the most important resonance structure I have is the one where the electron withdrawing group helps stabilize it. So I'll draw out the nitro group like this, and this will stabilize it in this way. And what we wind up with is this. All right, so this is showing the electron withdrawing group stabilizing that intermediate. I have other resonance structures where the negative charge is distributed on the other atoms. So all these 1-3 relationships where the negative charge is here, as well as the other resonance structure where it's on this carbon. So all these are resonance structures that are possible. This is the important one that shows the nitro group stabilizing that. And then what happens is we get elimination of our leaving group. And what we wind up with is the OH. And we reform the aromatic ring. And I'll get my nitro group back, and I'll have the Br minus as the leaving group. So typically this is done with a lot of base present, and if I have a lot of base, or a lot of hydroxide present, I'll get the protonation of my intermediate. And then I'll have to do a second step. So base is the first step. And I'll usually just do an acid workup to protonate it to get it to go to the neutral compound. All right, so here we can see why the ortho position is good. I have an intermediate that stabilizes that negative charge. That electron withdrawing group helps that negative charge be stable. So that's the ortho position. Let's look at the para position. And we're going to see a very similar thing. Right, so if I have the nitro group, and I'll have, in this case, I'll use a chlorine, and I treat this with OH minus as my nucleophile. This will be the first step. In the second step, I'll treat it with acid, and I'll wind up with overall Cl minus. In this case. So again, same thing happens. I get attack of the nucleophile. And here, it's not obvious right away, but I'll show you in a second why we get what we get. So the chlorine comes in here, the OH is here, and I have the negative charge on here. So right away with the para, it's not obvious how that electron withdrawing group is helping. But when I draw that first resonance structure, I can see I wind up with the negative charge right next to the electron withdrawing group. And that's the reason why this reaction works. So this is stabilized by the NO2. Right? And I could show the elimination, form the double bond, kick out my leaving group, and I re-aromatize to give the substituted product. All right, so we can see that the ortho and para give these nice stabilized intermediates. When I look at the meta, so I'll do a bromide, and again, I'll do the nitro group, and I'll try to do the addition with OH minus. Here we know we're going to get no reaction, and we're going to try to figure out why by actually doing the addition. So if this were to add, this would be the intermediate that I would get with the OH and NO2, and the minus charge is there. If I look at all the resonance structures of this molecule, all right, so let's go through and write them all out. I can put the negative charge here. And I could put the negative charge here. And those are all my possibilities. And I can see that every one of these, none of them are stabilized by the nitro group, by the electron withdrawing group. That's why we get no reaction in this. I don't get a stabilized intermediate, so no addition is possible.